Hi, I'm Krishna, and I shall be presenting our work on scaling generative pre-training for user ad activity sequences on behalf of my co-authors. Let's get started with a brief insight into why modeling user activity sequences is a good idea and highlight its usefulness to multiple advertisement applications. User activity sequences are simply a temporal representation of the user's interaction with an interface. As we're modeling the sequence itself, the input space of the model consists of event-level information as opposed to feature aggregates. Thus, in addition to providing the ability to capture finer nuances among sequences, this reduces the reliance on feature engineering. Both of these are desirable. Some of the downstream ad applications that benefit from modeling activity sequences are ad response prediction, where we're interested in predicting a response to an ad impression served, for instance, a view or a click. Personalization, where we're interested in serving ads that are most relevant to a user. And ad fraud or bot detection, where we're interested in safeguarding advertiser spend. While a deep sequence model, such as an LSTM or a transformer, could be a common backbone, the training techniques for models across these applications are differentiated by the extent of ground truth available. In tasks such as ad response prediction, where labels are abundant, supervised methods are typically used. However, in tasks such as fraud detection, where large-scale ground truth is unavailable, unsupervised or self-supervised pre-training methods are typically more effective. In this work, we are interested in the latter. Generative pre-training aims to model the input data distribution as closely as possible from the training samples available. This is achieved by training a large neural network on large unlabeled data using a proxy task that determines the training objective. Common proxy tasks on sequential data are mask token prediction and next token prediction. The key advantage of modeling sequences in such a manner is that they provide task-agnostic embeddings of the input, as they're simply attempting to model the input. The embeddings of the inputs can then later be used for several downstream tasks. Pre-training has shown to typically improve performance on both supervised and unsupervised downstream tasks. We now narrow down to the formulation of generative pre-training for user ad activity sequences. Our training objective is to predict the next event in a user's activity sequence using a neural network and is mathematically represented by the following likelihood function. As alluded to earlier, each event in the sequence has fine-grained information noted here as features. Assuming conditional independence among the features, the likelihood of the next event in the sequence can be written as the product of the likelihood of each feature of the next event given the previous events. For low cardinality features, we compute the probability using softmax. For high cardinality features, we approximate the probability using negative sampling and contrastive loss. Overall, this objective can be applied to any off-the-shelf deep sequence model. However, our experience shows that transformers scale better. Given the pre-training setup, we are keen to understand its scaling properties. That is, investigating how the model performance improves with increase in three broad parameters, namely model size, data size, and compute. As we scale each of these parameters, we measure performance in terms of test loss on the pre-training objective. In addition, we evaluate how this improvement in test loss on the pre-training objective translates to performance on two downstream tasks. Let's begin with the effect of model size on test loss. We only consider the non-embedding parameters in the count, and our range spreads over 3 orders from 10 power 5 to 10 power 8. In this experiment, we train on all available data in terms of number of users in the ad program. Our main observation from the graph on the right is that the test loss follows a power law relationship with the non-embedding parameter count, and that we are able to predict the performance of a larger model by extrapolation. However, we note that this trend will saturate at some point due to the bounded dataset size, as increasing the number of users in an ad program is not trivial. Next, we move on to data scaling, where we are interested in the effect of the number of user sequences used during pre-training on test loss. For a fixed model size, we train on 0.1%, 1%, 25%, and 100% of the user sequences available. We repeat this over 3 model sizes and plot the same in the figure on the right. Our first observation is that larger models are more data efficient. That is, they require lesser data to achieve a target test loss. As shown in the figure, for a target test loss of around 7.8, the 12 million parameter model requires 1% of the data, while a smaller 410K parameter model requires more than 10 times as much data. Our second observation is that smaller models benefit more from increasing dataset size than larger models, as pointed out in the left extreme and the right extreme part of this graph. Finally, for a fixed model size, increasing dataset size gives diminishing returns. The figure on the slide highlights this observation for one specific model size. Thus, our key takeaway is that the model size and data size have to be increased in tandem to maximize performance. However, as alluded to earlier, dataset size in user ad sequences is generally bounded in terms of the number of users. Thus, we suggest training the largest model given a compute budget. From the previous two scaling properties, we have established that scaling both data and model size in tandem maximizes performance. However, in practical industry settings, training of models is bound by monetary constraints. The monetary constraint dictates the compute budget available. We use wall clock GPU hours as the measure of compute, as against standard petaflop days, as the monetary cost incurred to train a model in a standard cloud setup is typically a function of wall clock GPU hours and not GPU utilization. Now, given a fixed number of GPU hours, there is a choice to spend them on either the number of GPUs or the wall clock time. In other words, this translates to a trade-off between serial gradient steps, model size, and batch size. In analyzing this trade-off, we maximize GPU utilization for all model sizes by choosing an appropriate per GPU batch size. Thus, picking a certain model size fixes a per GPU batch size as well. We then choose 4 compute configurations that define the number of GPUs and wall clock time while keeping the product or the compute budget constant. A higher number of GPUs in a certain configuration translates to a larger global batch size used per gradient update, whereas the wall clock time defines the number of gradient updates possible within the compute budget. This is done over different model sizes and plotted in the graph on the right, from which we derive 2 key insights. First, larger models are more sample efficient. We arrive at this by observing the trend for any compute configuration across model sizes. We note that larger models show a lower test loss, but I would also draw your attention to the fact that a larger model size implies a lower global batch size given the same compute configuration. These together lead to the inference that larger models are more sample efficient. Second, for a fixed model size, increasing serial gradient steps or wall clock time is more effective than increasing batch size, as configuration 4 outperforms configuration 1 across all model sizes. Thus, to summarize, at a constant compute budget, it is beneficial to increase model size, decrease batch size, and increase serial gradient steps. While the trend of decreasing global batch size seems to be beneficial, an overly small global batch size would lead to noisier gradients. This points to the existence of a B-min global batch size. We empirically demonstrate this in the table on the right, wherein, at a constant compute budget, a larger model with a global batch size less than B-min will underperform a smaller model. Thus, it is crucial to scale the model size, keeping the global batch size at least B-min. But increasing the model size also leads to a reduction in the serial gradient steps at a constant compute budget. This is of importance because there exists a W-min which we define as the minimum wall clock time required for a larger model to outperform any smaller model. We show evidence of such a W-min in the graph on the right, where even though we give the smaller model a sizable advantage by keeping the batch size closer to B-min, it is outperformed by a larger model with a much larger batch size after a certain wall clock time. Thus, the key takeaway is to increase the model size until the extent that both B-min and W-min are within the compute budget. We show this in action in the table on the bottom right, wherein we are able to achieve a better test loss from a larger model in a fraction of the training time at the same compute budget. Until this point, we have discussed the effect of scaling on the test loss of the pre-training objective. Here, we show that improvement in test loss on the pre-training objective translates to improved downstream task performance. We consider two downstream tasks in ads, namely conversions prediction, which is a supervised task over the embeddings, and bot detection, driven by unsupervised clustering over the embeddings. The table on the right shows that for both these tasks, lower test loss was obtained by larger models in the model scaling section translates to improved task performance. The conversion AUC rises as much as 3.5% and bot recall by as much as 4% when increasing the model size by 3 orders. On further analysis, as shown in the figure on the right, we observe the lift in the performance on bot recall to be focused on low-click bots, implying that larger models have better representation learning with limited data. To conclude, we showed that pre-training test loss follows power law scaling with increasing model size. We also showed that larger models are more data and compute efficient. While we were able to predict the pre-training test loss in model scaling via extrapolation, we observed that the downstream task performance doesn't follow power law, but will likely improve. We also discussed that increasing dataset size arbitrarily is not trivial in user ad activity sequences, but we show that this is not a key constraint at model sizes considered, as the test loss did not saturate even with 1% of the user sequences. Finally, compute efficient training need not converge under the condition that the model size was scaled while accounting for a minimum batch size and a minimum wall clock time. Thank you, and please reach out to us for any questions.